Hey everyone, Morgan here. We're on page 4 of the AP Chemistry lecture outline dealing with thermodynamics, and we're going to take a bit of a statistical view of nature today. Now, none of the historical stuff involved here is on the AP exam, and we might start to get into some of this dealing with the Chemistry Olympiad, but there's some interesting history that goes on with this that I'd like to point out. The first person that really comes into play with this discussion is Ludwig Boltzmann. And Boltzmann was born in 1844 and died in 1906, maybe 1907, somewhere in that area. He was an Austrian physicist well ahead of his time. He was one of the first, what we might call atomists, one of the first people that really believed all of nature was composed of smaller particles, which we now refer to as atoms. Okay? We'll come back with him in a bit. Now, Walter Nernst, 1864 to 1941. Nernst helped to contribute to these ideas with his discussions on something called the Heat Theorem. And basically it says at 0 degrees Kelvin, heat capacity vanishes. And that would actually make sense because we know heat to be a transfer of energy between two objects at different temperatures. And it is the movement of the kinetic energy between the two objects that moves that heat. And if you're at 0 degrees Kelvin, you have no molecular motion. Okay? Now, in the period of like 1906 to 1912, give or take, he developed a lot of this material. And if you've had a little bit of calculus, what we can say is that the limit as temperature approaches 0 for the change in entropy is going to equal 0. Okay. About 1910, Max Planck. Let's see, Planck was born, I think, about 1856 and lived to about 1947. About 1910, Planck was applying ideas from the Heat Theorem, okay, and expanding all of this, okay? So it really started to come together, all of these ideas, with Linus Pauling. Pauling was born in 1901 and passed in 1994. In 1925, working with Richard Chase Tolman at Caltech, Pauling applied these ideas to crystal structure. And out of that was born what we will call the third law of thermodynamics. Now, Boltzmann's equation is used to calculate entropy, and it says that S equals K times the natural logarithm of W. Now, K is the Boltzmann constant. It's basically just the gas constant R divided by Avogadro's number. And that equals 1.38 times 10 to the negative 23rd joule per Kelvin. Okay? Now, W is the number of ways that we can put a crystal structure together. It's a permutation. Now, if you can only assemble a crystal one way, the natural log of 1 is going to be 0, which means it basically has no entropy. But as you increase the number of ways that you can assemble the crystal, you're going to increase its entropy. Now, Pauling took that idea into this wording of the third law of thermodynamics. It is acceptable to define the entropy of a perfect crystal to be 0 at absolute zero. Now, the interesting thing about this, he's not saying its entropy is zero. He's saying we can define it to be zero. And in fact, you can have something on the order of 10 to the 15th, which is a huge number, 10 to the 15th flaws, and when you do this calculation, because of the value of K being so small, the entropy would still be zero. Okay? A perfect crystal would be a crystal that has no flaws. They do not exist on planet Earth. However, we can grow crystals up in outer space, the International Space Station. And because there's only microgravity affecting them up there, we get crystals that are practically perfect. Okay. Now, we've talked about the first, second, and third law of thermodynamics. It turns out that there's a prerequisite for all of this to be true. And if this prerequisite doesn't hold true, all of the laws of thermo fall apart. For that reason, they called it the Zeroth Law of Thermodynamics. It says if system A is in thermal equilibrium with system B, and system B is in thermal equilibrium with system C, then system A is in thermal equilibrium with system C. That sounds a lot like the transitive property from geometry, doesn't it? Okay? And this establishes the linearity of the temperature scale. That on the absolute scale, Kelvin scale, something that's 300 Kelvin is hotter than something that's 200 Kelvin. We need that to hold true. And it's prerequisite. U-E-S-I-T-E. Sorry about that. Okay. So, those are the laws of thermo. And with everything we've established now between pages 1, 2, and 3 of this outline, I wonder if you actually remember the question that we set out on page number 1. And that question is, if left to itself, will a given reaction happen without outside influence? And we are going to use the concepts of enthalpy, entropy, and temperature to answer that question. And that will all start on page number 5. Thank you for tuning in. This is Morgan signing off.